Okay, I think everyone can see the slides, yes?
Yes.
Okay, so I'll do a quick substitution talk before we move to the next speaker. So the topic of this talk is Bose-Einstein condensation of rapidly cooling Magnon gas in antiferromagnets. And so the Bose-Einstein condensation of magnets is basically the phenomenon when magnons, they accumulate at the bottom of the Magnon spectrum, and then they basically all go to the same Magnon state. And this means that Bose-Einstein condensation, because this is coherent Magnon state. And this phenomenon has been observed in ferromagnets. Basically, here you can see the figure that shows experimental results, where we have this ferromagnetic sample, then we apply 120 nanosecond heating pulse, and this heats up the ferromagnet. This increases the total number of magnons in the sample, and then we rapidly cool the sample down. During this rapid cooling, the magnets that were added by the heating pulse, basically additional thermal magnets, they quickly become non-equilibrium magnets. The thermalization process starts, and during this thermalization process, accumulation of magnons at the bottom of the spectrum happens, which leads to increase of the chemical potential of the Magnon gas, which leads to Bose-Einstein condensation. And here we clearly see the increase of the presence of the magnons at the bottom of the spectrum and increase of the chemical potential up to the minimum of the Magnon spectrum. And the idea of this research is basically to see if we can achieve the same effect in antiferromagnets. So here we see like the sketch of the spectrum of antiferromagnet, only one branch of it. And technically, if we can get a significant accumulation of magnets at the bottom of the spectrum here, which corresponds to increase of chemical potential up to this spectrum gap, then we can achieve Bose-Einstein condensation of magnets. And in this, while considering the thermalization process of magnets, we used a quasi-equilibrium approximation when we were describing the magnets. So basically, we describe the Magnon gas with a certain effective temperature and the effective chemical potential. And quasi-equilibrium approximation means that the thermal magnets which interact with each other so fast that we can neglect this interaction. Basically, the Magnon gas is always in quasi-equilibrium, and we only focus on interaction of the Magnon gas with the lattice. And therefore, we can describe the populations of magnets with Bose-Einstein distribution, shown here. And then we describe this whole system in a thermodynamic way. Basically, we consider the total number of magnets in the Magnon gas and the total energy of the Magnon gas. And here we consider also density of states. And for example, we consider density of states of nickel oxide as antiferromagnet. And then we can write down equation of motion that describe the change of total number of magnons and total energy of the Magnon gas with time. And if we simplify the way it looks like, it's actually a simple system of differential equations. And however, which can be transformed into the system of equations for temperature and chemical potential. Then, during this simulation, we also introduce the rapid cooling of the lattice. And we could use the just linear cooling. However, the cooling of the antiferromagnet must be very fast, and at these small times, these peculiarities of cooling can be important. And we utilized the exponential cooling instead of a linear, the specific cooling time shown here. And from the results, we can see that as we decrease the cooling time, the faster we cool down the system, the more rapid the cooling, the greater the increase of chemical potential, and at some point the chemical potential will increase up to the spectrum gap. And in these simulations done with equations for temperature and chemical potential, we see this artifact that part of it is missing, and this is because the chemical basically this system modifications is very bad for simulating specifically region at the chemical potential being equal the Magnon gap. And instead what we need to use is equations for total number of particles and total energy as was in the beginning. And using these equations we can achieve proper simulation. So basically, when we cool down the antiferromagnet fast enough, the chemical potential reaches the minimum of the Magnon spectrum. And for short time, we have formation of Bose-Einstein condensate. And here we can see example of the pulse of the Bose-Einstein condensate formed as a result. And in summary, you can say that chemical potential is not suitable parameter to simulate evolution of the Magnon gas in the region of Bose-Einstein condensate formation. And we use total energy of the Magnon gas and the total number of magnons in the Magnon gas to describe the system. The method proposed allows convenient description of a Magnon gas dynamics, and this research was sponsored by the Murie Grant from the Air Force Office of Scientific Research. And that's all for this presentation. Thank you for attention. So if you have quick question, I can answer it, and if no, we will move to our next speaker to keep the schedule.
Yeah, thanks, Pedro. Very interesting stuff. So I have one question, quick question. So in Bose-Einstein condensation or the thermal excitation, Magnon excitation, do you or can you figure out the Magnon modes, which Magnon modes you're exciting in your system?
So basically, you ask him if you can see where the magnons accumulate.
Yeah, kind of, and the Magnon mode, because there are in antiferromagnets, the different kind of you have a different modes, in-plane modes, out-of-plane modes, collinear mode, kind of modes.
Okay,
and which
I
Magnon
understand.
mode? Yeah.
Okay, I understand. So here we do not differentiate between different types of modes, as you say. So the idea is, so basically here we work with thermal magnons. We do not excite additionally magnons. Basically, it's all thermal magnons.
Yeah.
We just get a sample of this ferromagnet or antiferromagnet, and we just work with it. We do not propagate spin wave through it. Non-additional excitations, just thermal magnons. They are present there. Okay, we heat it up. We add more thermal magnons. We rapidly cool it down. Those magnons suddenly become.
So it's kind of a broadband excitation, kind of.
So this is like a thermal excitation, which excites, one could say, all the modes, all the thermal magnons.
It's a broadband excitation process, kind of. Thanks.
May I ask another questions? A quick one.
Okay, if no questions, then I will stop sharing the screen.
Oh, may I ask a question?
Yeah, you can. You can. Yeah, you're next speaker. But yeah,
so, yeah. Typically, the condensation survive more than 100 nanoseconds, and I saw that your condensation just survived, say, sub-nanoseconds. So what do you need to do to make some state condensation the lasting more than, say, 100 nanoseconds? Okay,
so the thing is, the 100 nanoseconds time is the one from the first picture, the experimental one. Yes.
Yeah.
So the thing is, here the time, how long the magnets can survive in the condensed state, it depends on the material. And here, when we say about 100 nanoseconds there and 0.1, let's say, nanoseconds here, we compare completely different materials. So in ferromagnets, the frequencies, resonance frequencies are gigahertz, and magnets, they interact fast. In antiferromagnets, magnets interact even faster. So exchanges, there's even more exchange, and the frequencies are higher. So I cannot tell you like right now the way to make a long-term Bose-Einstein condensate in antiferromagnets, but it's very short time due to material properties, just because it's
Okay.
antiferromagnet, not ferromagnet.
Okay, thanks.